Hi and welcome to my channel. Today I'm going to take a look at one of my prized possessions, my HP 5245L counter. The 5245L is a DC to 50 megahertz counter. It was first built in 1965. The list price on this guy was $2,950 US in 1965. That's the equivalent to about 22 grand in today's money. But you know, for that sort of cash, you get this beast, which compared to what you can find today is considerably more substantial. I checked on eBay and looked for counters with similar specifications, and you can pick up something for about 10 bucks. But you know, mind you, they don't really have 50 pounds of aluminum, glass, and steel, you know, in their manufacture. The 5245 is still a useful tool 51 years later. Its main limitation is its low top frequency of only 50 megahertz. But for a lot of ham radio use, retro computing use, 50 megahertz is plenty of bandwidth to do your testing. So it's actually a pretty useful tool. There's also an upscaler module that will bring it up to, I believe, 3 gigahertz. However, using it's a little bit weird and it's not super useful, so I wouldn't recommend this as a high frequency counter. It's better within its 50 megahertz range. The machine itself has a built-in frequency counter. It's got period counter, period averages, all sorts of different functions, and I'll go through a few of those functions and then I'm going to tear it apart and show you what's inside. Okay. So here the counter's been powered up. I've got an input signal. There's nothing actually being input right now into the input signal. You can see here there's a sample rate control, sensitivity. Sensitivity can either be plug-in, which means use the inputs on this plug-in side, and I'll get into that in a second. 0.1 volts, 1 volts, 10 volts. One thing that's interesting is the voltages used on these counters are quite high. So having a 10 volt scale is actually something you wouldn't use very often nowadays. But back in the 60s, you know, there was a lot of electronics running at 12 volts, even higher voltages, and you would want a higher scale there. Here you can see the gate. This is closing every time the gate finishes counting, so every period. Here's the time-based control. Time base is currently set to 10 seconds, and you'll see the gate is open for roughly 10 seconds. It's going to flash. So there the gate is going, and it should flash in a second. Flash, there we go. So I can switch that to 1 second, so this will be now a 1 second pulse on the gate. A tenth of a second, 10 milliseconds, and lower and lower and lower to the 1 microsecond range, or even 0.1 microsecond range. Reset is used for your single count modes, and then there's various functions on the counter itself. So there's a frequency count, which is, you know, the most popular function that you would use on something like this. There's a manual count mode, so you can do counting functions. So if you were using this as a tool to say count number of cars passing a location on the road, you could use that in order to do this. There's period average, so the period between pulses, and that's basically it. Great thing, of course, about the counter is that it's all Nixie tubes. Nixie tubes look awesome. We'll pull it apart. We'll take a look at those. The lights are all neon lamps. It looks great as a counter, and the fact that it's still as useful as a tool, you know, makes things even better. On this side we have a plug-in module, and this is pretty cool because there's a bunch of different options that you can get for this counter. One that I mentioned earlier was a frequency upscaler to bring it up to 3 gigahertz. The one that I use the most is the video amplifier. This is very useful today because, you know, your minimum sensitivity here is 0.1 volt, whereas on this one you can go down to 1 millivolt sensitivity, and for a lot of applications you really need that sensitivity. So if you can find one of these along with a counter, you're in good shape. This particular one I picked off of eBay. It had been sitting on eBay forever, and I bought it for $5. And I actually apologized to the guy. I said, hey, you know, sorry I'm buying your thing for so cheap, but you know, rest assured it's going to get a lot of good use. So I'm going to pull this module out, and we'll take a look at it. So you can see here, well, there's actually some nice stickers, HP service stickers, and oh, US Air Force, cool. Last calibrated in 1985, October 1st, 85. So it's been a while, but this is a former Air Force property. I bought it fair and square, so US Air Force, please don't come after me. Well, we got our power meter here. We've got a 50 ohm output and a 1 mega ohm input. Our sensitivity control here. And then inside we've really got a circa 1965 circuit board here. You can see there's actually, what's really cool about this thing is that there are transistors here. Like this little guy's got a little heat sink on it, each individual transistor with heat sinks on it. You got to remember at this time the transistor itself was like 8 years old. Transistors were not used, generally speaking, in consumer goods yet. To have something that was transistorized was actually a pretty big deal. So HP, you know, this is cutting edge for 1965. Old school capacitors there, great stuff. If you take a look inside here, well, there's a big shielded box. I'm not going to pull that apart. I don't want to go in there. And there's an adjustment right on there. It's quite neat. And then at the back, we've got a, looks like a 68 pin header, which is for the plug-in module. So that's your HP 5245 plug-in. Pretty cool stuff. I mean, I really think they were thinking ahead when they built this. And here we've got inside the unit, and you can see the header at the bottom there, and some adjustment points there, which I don't actually know what they do, but you can see where that mates inside the counter itself. Oh, it's quite a robust little connection there. Okay, so let's do a quick test of the counter itself. I've got it plugged into a 5 kilohertz input signal, and as you can see, when the gate opens, it counts the frequency during the gate open period, and then it'll settle on that 5,000 number. You can adjust the sample rate using this control. So I slow it down and it will hold it, the gate won't open, and it'll let me view the count for as long as I need to view the number. Here's another test. I've set my frequency generator to 5 hertz, and you can watch this manually count up 1, 2, 3, 4, 5 as it goes along. So now I'm going to do a 1 megahertz signal, just so you can kind of see the difference. 1 megahertz here, and it will count in a moment. And we can see 9999999. So that's normal that you would be off by one number. 1 megahertz exactly. One of the things I like about this counter is that it shows you what it's doing while it's actually counting, which is a cool feature as far as I'm concerned. A modern counter won't have that. It'll just display the results after it does its sample period. Now, the 5245 has a mode called storage mode, which you can turn on with a switch in the back, and that will make it, you know, basically work in the same way that a modern counter will work, whereby it just shows the results after the gate closes. So what I'll do in this case, I've switched it over, and you can see it's staying stable at roughly 1 megahertz. I'm going to move my frequency generator to 1.1 megahertz, and we'll just see the results there. So first sample it's off, and then second sample it's stabilized, and now it's 1.1 megahertz. Or as it's displayed on this screen, 1100 kilohertz. So on this side we've got options for our frequency standards. An input's on this side, and you can either use the internal or external source here. And there's an output on this side, so you can use the internal source as an output to use as a standard frequency for the rest of your equipment, which is a great option. I've got it set to 10 megahertz. This allows you to select a number of different frequencies, and now you got to remember in 1965 they hadn't really standardized on 10 megahertz as a signal standard, and you know, so they give you a bunch of options. If you look at HP equipment from this era and into the 70s, a lot of it will work off of a 1 megahertz signal. Some will work off of 5, which this doesn't have as an option, and some will work off of 10, which they eventually standardized on. So it's nice to be able to use this as a frequency standard, though, so all of your equipment agrees with each other. Fan here, it's a little beat up, this screen. And then on this side, we've got storage mode control, so it can be either off or on. And then you've got this digital recorder port, which is really cool. Digital recorder allows you to take whatever's being measured on the counter and output it to external devices. And this is really the start of GPIB right there. So the standard that is used, you know, largely till today, was actually started, you know, about 50 years ago with this HP equipment, and it was known at the time, and it was known, you know, into the 70s and 80s as HPIB. Now they call it GPIB. Started to get replaced with USB and whatnot, but this was really the start. Now here I've got a nasty power cord bodge, which is pretty bad. But what I did is I took an old power cord and wired it directly into the counter. Reason being, this plug that they use is extremely rare. I couldn't find any. I eventually found one about a year after I bought this counter. So I came up with a horrible hack, and I used this nasty little connection here with a zap strap in order to work as a strain relief. Okay, it's not great, I admit it, but it works. So it's going to stay like that for now. On the side of the unit, there are classic HP handles, so you can lift up this 50-pound monstrosity. These are like super rugged, so that's pretty cool. One on each side. And to open it up, we've got these two screws here, which I'll pull apart in a second, and we'll take a look inside. Okay, so let's open this guy up. Screws are locked in place with a spring, so they turn, I think, one rotation, and it pops up, and then the case is open. And inside we've got some nasty 50-year-old foam there, and oh, there's the number there, 13749. Not sure exactly what that's all about. And it's an interesting color. It's like a gold color that they've got here, and I don't know what that paint is, what the material is. I mean, maybe it's anodized aluminum. That's what it probably looks like. Some sort of anodized aluminum. Oh, pretty cool. Anyways, there's the top. And inside, oh, we've got awesomeness right there. You can see. So we can see our fan, the back there. Very old school fan. It's loud too. A couple of, well, 3 massive capacitors right there. Transformer, a couple more massive capacitors. Good chance to get electrocuted. I got to unplug this thing. We've got several boards here, and then here we've got something very interesting. This is a crystal oven. So there's the frequency standard for this is based on a quartz crystal, and in order to maintain the accuracy of that quartz crystal, it is kept at a continuous temperature of something like 70 degrees Celsius. That gives it, you know, pretty exceptional stability for a quartz crystal based frequency reference. So that's quite cool, and it's a totally sealed unit. You can see here there's power coming in. This here is a capacitor, so that's obviously adjustment for frequency there, fine tuning. And you know, it's really a sealed unit that is just got a temperature. It's got a heater in there, temperature sensor, and that keeps the crystal at a consistent temperature and therefore a consistent frequency. Interesting note is that a quartz crystal apparently gets more stable as time goes on. So seeing this is 52 years old at this point, mine should be pretty stable. I don't know how much that helps. So at the front we have our frequency counter boards. These are simple 1 to 10 counters that are daisy chained into each other. There's 8 boards, one for each Nixie tube, and they're basically chained into each other. When they roll over, it causes the next board to count 1, etc., etc., etc. I'm going to pull those apart, and we'll take a look at them. So there's a nice aluminum bar here holding everything in. I got a couple of screws there. There. Pull that apart, and let's pull the board out, see what we get. There we go. Got it, and yeah, nice. You can see the nice connector there. That is actually probably quite ahead of its time, having that sort of bus style connector. Not a lot of electronics at this point in time would have that type of circuit board and or edge card connector. Most consumer stuff would be point-to-point wired. So this is, you know, really high-tech stuff for 1965. There's a bus connector at the bottom there, nicely labeled, which is great. And we can see here is the counter itself. This is one of the counter boards, and you can see it's got a transistor-based counter on this side. Pretty straightforward, and these are like quite old school transistors. Like if you look at the casing in them, they're really big. 3 pins still, so it's a pretty standard device, it seems like, but I'm not sure what that case style is. Again, like I said, you know, transistor was only 7 or 8 years old at the point where this was built, so that's pretty high-tech stuff right there. And all these resistors, you can see here, they're the old ceramic style resistors, and they've got painted stripes on them even, so it's quite cool. But the manufacturing technique is also, like I said, super modern for 1965 because it's actually on a PC board. There's traces, you know, on both sides of this board. It's a single layer board. It's not copper, it's like maybe it's tin or something like that for these traces. It's quite cool. And you can see that the leads themselves, they've all been hand clipped because they're all different sizes. Very interesting. There's a date stamp here, tested September 1967, so that's cool. I've seen some of the boards in this are dated 1965, so I don't know if this counter was you know, 67 vintage, or this is a replacement, or who knows what, but it's quite interesting. On the board we've got, you know, our Nixie tube on this side. This is the plastic itself is like a Bakelite. It's very brittle. I've broken a couple of pieces of this, disassembling them and reassembling them. So you got to be careful about that. This box here is quite interesting. This is a memory. So if you think about it, a counter, I showed you the counter and how it displays the current value being counted as it goes along. Doing that is pretty straightforward. You just use the counter circuit. But if you actually want to store the number and have that storage mode like a modern counter does, you need to have a memory of some sort. It needs to know what the last value was. The way this counter is built is there's individual modules that count up to 10, so each module needs to remember where it was from 0 to 9 while it's counting up the next number. And the way it does it is with this module. 1965, memory modules would be created with core memory typically. So that's a magnetic loop that has a couple of wires going through it that you magnetize, and you can use that to determine you can use that to store a byte you can use that to store a bit in memory. The HP counter uses a different technique, which is neon lamp memory, believe it or not. In this unit there's 8 neon lamps, and there's also, I believe, 12 CDS photocells, which are used to complete the circuit for the Nixie tube. So how can you use a neon lamp as memory? Neon lamp has a property called negative resistance, and essentially the gist of it is that the neon lamp fires at 70 volts, and it will remain lit up to, as you crank the voltage down, to about 55 volts. So when it's lit, it conducts electricity. When it is not lit, it doesn't conduct any electricity. So what you can do is you can fire the neon lamp using a 70 volt signal. It lights up, and then you start passing in, say, a 60 volt signal into that lamp. If the voltage goes through the lamp successfully, then you know that the lamp is lit. If the voltage doesn't go through the lamp, because it's below the trigger voltage, you know that the lamp is not lit, and therefore you have a bit of information. So there's basically an array of neon lamps inside here that you can't see, which light up and store the last state of this entire counter board while it's recounting. Then those neon lamps are directly placed near CDS photocells, an array of CDS photocells, and those CDS photocells cause the circuit for the Nixie tube to light up appropriately. So it's a really cool solution for memory. You know, in 1965, they didn't have, you know, a lot of options. There were no RAM chips, so it solved the problem, and it's quite neat. Now I wanted to take a quick look inside here. Just you can see the multiple boards, counter boards there, each one. I've got, here's some of that Bakelite plastic that's broken, that cracked. I cracked it. Not very happy about that. There's more here, cracked as well. It's quite brittle after 52 years, so it's you know, not in the best of shape. And then here's the bus system for the board itself. I just wanted to show those connectors. One thing to note about this is that there are high voltages in this counter. The counter, the Nixie tubes are running at about 170 volts, and the neon tubes are running at about 70 volts to 60 volts, depending on what's going on. So you can get yourself nice and electrocuted by touching those things while this unit is on. So be careful if you have one of these. You know, be careful you're playing inside. You could zap yourself. Especially be careful with the capacitors here. These are massive capacitors on a big power supply, and if you were to touch the two contacts on the bottom of this thing, you could kill yourself, even if it's unplugged. So they need to be fully discharged in order for you to really play around with them. Okay, so let's power this thing up again and just take a quick look at the system while it's running. You can see the front there, we've got our nice Nixie tubes all lit up. Very pretty to look at. Let's get a really close in shot. You can see those. And the Nixie tubes are basically neon lights that are encased in a single glass tube, and each digit is built out of a wire that's been twisted into the shape of a number. So you can see as the numbers go from 0 to 9, where they actually light up physically in the tube, it goes back and forth, which is quite cool. I mean, this is awesome retro technology. Nixie tubes are still available. There's new old stock that's out there. There's not a lot being manufactured, but there are some being manufactured still in Russia, as far as I know. There's a lot of stuff from, you know, the Soviet Union that's new old stock that you can get. So they're still available. I actually got the replacement for this digit here as new old stock from a local provider, which really helps out with the look of the unit. Going to the back, the other interesting thing about this is that fan. It is super loud. It's basically like a, you know, 1950s desk fan almost, is what it seems like. It's very robust. I actually think I might replace that with a more modern fan and just save that somewhere, just because it's actually so loud, and using this in the lab day to day, it's a bit loud to keep running. These backboards here are all amplifiers and whatnot for the input signals, and there's also amplifier boards for the output signal for the frequency standard. So that's what all those boards have for functionality. And on this side, I'm gonna guess that this is our power supply. So we've got, you know, a bunch of big capacitors there, resistors. I'm not sure what that AB thing is. It looks like a variable capacitor, or sort of a coil. Can be adjusted. Quite interesting. All these components, because they're so old, they don't look like modern components, but they're sort of a variation of components you may have seen in, you know, 70s and 80s equipment, except they're sort of the big old original version of them. And again, the thing I find fascinating about this is that it is really one of the first pieces of equipment that has, you know, modern production techniques, you know, quite modern components, as opposed to being point to point or using, you know, a lot of vacuum tubes and whatnot. So it's quite an interesting piece of history as well. And just one shot here, I wanted to get the 5243A69A crystal oven. I mean, hey, who has a crystal oven in their house? I do. You could too. Here's just another shot of some you know, nerdy, ooh, this is great stuff. HP used to be a awesome company. Used to be the best company in the world for test equipment. You know, before they started to get into the printer ink business, they made the best test equipment, and that's what built the company. Hewlett-Packard in their garage in Silicon Valley, and they founded Silicon Valley essentially. This used to be something awesome. HP nowadays is pretty much crap. Well guys, thanks for watching my video, and I hope you enjoyed it. If you want to see more content like this, make sure you subscribe below, and if you have any comments or questions, comment away.